it's not like in a normal building where you have to take the stairs in case of an emergency, because the lift is a safe area. It's overpressured, the whole system is overpressured, so no smoke or fume can go inside. And the other side, the stairs are not overpressured. So it's dangerous because in case of a fire, for example, it will work like a chimney. So the lift is safe, and also the areas in front of the lift are safe. The rooms in front, so it's a secure area. You can also wait for the lift in case of emergency without being danger. Okay. So it's just an exception for visitors, but I have to be scanned, so I'm now responsible, and they have registered me, and so it's really everything is secured and observed.
Tiene que estar pendiente del rebaño y así el sistema sabe quién está dentro de cada momento. Si hay una emergencia y vienen los bomberos, as when the fireman brigade, they know who is down there, precisely because everybody is registered there. Entonces cuando ellos vienen, lo primero que información que ya tienen por el camino es quién está abajo, cuánta gente hay, cuántos grupos y lo que están haciendo.
Like basic groundwater, but a real river, underground river. So it was the civil engineers kind of said, "You're crazy. You cannot dig a hole here. It will get full of water." So they had to froze the ground all the way down the 100 meters, and then they have dug the hole through the frozen ground, then covered it, and now it's water floating around it. Okay. It's complicated, but it's really important. We collide protons with a rate of 40 million collisions per second. 40 million collisions per second. Each collision produces a data volume of 2 megabytes. So we have 80 million megabytes per second. And we are running each day 20 hours for years. It's too much information. We cannot store it or compute it. So we have to decide which events will we keep and which can be deleted. Because most of these events are not interesting. It's garbage. Or we already know so much about these processes that we're not anymore interested in them. So something like the Higgs boson is really a rare process. It's not so likely that it's produced in a collision. So it's not a big problem to delete most of the collisions. But we have to decide which one to delete. And in this time, this device has to make a decision to keep or to delete. And it's not much time. And it's too less time for normal computers. So what we have here are programmable hardware. The algorithms are implemented directly in the hardware on the circuit board. So this can make the decision really fast, but a simple kind of decision. We are only looking for two different criteria. It's if we have a huge computation grid all over the world, the worldwide computation grid, which has a huge computation farms in many different countries, and the data are stored everywhere, distributed, and if you want to analyze the data, you can assess this complete grid. Every physicist can use Detector CMS, can assess all these computation powers. We have something like 20,000 CPUs we can assess to use this data. And yeah, that was a huge effort to be able to deal with this huge amount of data, but it's worked quite well. And have you any idea why we need a laser system as our detector? Some ideas.
¿Por qué necesitamos un sistema de láseres?
¿De láseres?
I know.
Yeah. Okay. Two reasons. First, we need a laser to calibrate our electromagnetic calorimeter. We are using the laser to shoot inside the crystals. Do you have thought about the crystals? Yeah. We are measuring the energy of particles with a material which is called lead tungsten.
Lead tungsten. They know it
tungsten.
even in Spanish. Wolframato de plomo.
It's most similar to German, Bleiwolframat in German. Yes.
Wolframat.
Yeah, and it's a really dense material. It's like a lead, but you can see through it. It's like glass.
Transparent, yes.
It's transparent. So if a particle hits this material, it will be stopped, and it will emit all its energy as light. This light then goes through this crystal and will be collected at the end. And then we can say, okay, we have so and so much light. This means the particle has shown so much energy. But we have to calibrate the response. Energy in, light out. And so we use a laser to shoot in the crystals, and with a defined energy. We know the energy of the laser, and then we can see the response and use this to calibrate the system. And this is done on runtime. In the spaces between the collisions, these 50 nanoseconds, the laser will fire. So, to calibrate.
So it's really often?
It's really often.
Yeah, it's a constant calibration.
We have to do it constantly because due to radiation damage, the crystals will be becoming less transparent. And we have to correct for this loss of light due to less transparency while it's running. And so the laser is shooting in between these collisions. The second reason we need a laser is CMS can be opened. You will see it later on. It is opened at the moment. Normally it's a compact, something like a barrel, but you can. It's built in slices, and you can open the slices to work inside. But afterwards, you have to close it again before you can start the measurement. And this closing has to be really, really precisely within the tolerance of a few microns, or even less. And it's only possible because we are guiding these huge slices with lasers while we close it. Just to get a feeling for it, one slice is something like 2,000 tons. The weight of one slice, something like 2,000 tons. We have to close it within a tolerance of a few microns. Okay. You can see here it's a complete accelerating complex, but we don't only have the Large Hadron Collider with this circle, but a lot of pre-accelerators. It's important because it's like in a car, you cannot start with the top gear. You have to accelerate first in smaller accelerators. If the particle has a certain amount of energy, then you can go in the next stage. And each of these pre-accelerators was their own experiment in the past. For example, the proton synchrotron was something CERN started with in the past. It was a really important experiment. Then there's a super proton synchrotron, that was from the 70s. There was the Z and the W boson was discovered there. It was also it won Nobel Prize, and in this case, really for CERN and not for the theorists. And then now there's the Large Hadron Collider, and maybe in the future sometime the LHC will be the pre-accelerator of an even bigger. Maybe. Okay, so here's the last place one can go when the machine is running. Beyond this point it's too dangerous because of the radiation. As you can see here, close. Because while the machine is running, there's a lot of radiation producing in the collision. And it's too dangerous, but at the moment it's fine. But if the machine is running and someone opens the door, a general shutdown will be triggered. The complete machine will be shut down. It's a really, really big problem. But there's a camera, and they will find you, and then you have a problem. But at the moment, it's not a problem. Please go.
Sí, sí, que se vea natural.
this part is pushed inside this part. This is the so-called end cap, and that is our barrel part. It's like, it's symmetrical on this side and on the other side. It's really looking like a barrel. And it's important that we cover almost the complete area around so that no particle can escape undetected. You can see the different subdetectors. In the outside, between the red nut, are these silver boxes. These are the muon chambers. The device is designed to detect muons. It's the same there, also these boxes. The geometry is a little bit different because it's facing on the other way towards the interaction point. The collision, or what you call the interaction point, is where the collision takes place. It's in the middle. Then the particles go out in every direction, and in this area they will hit the detector that way. And in front they will hit the detector that way. This is because why these boxes are facing this way and here this way. Around these boxes, the red stuff, that's just iron. We need this iron for our magnet. The magnet is this silver ring you see in the middle. Inside the magnet, it's a strong magnetic field of 4 Tesla. It's a homogeneous magnetic field. But it's from the principle, it's just a coil. And in the outside, this magnetic field will return to the other side. And it's normally a mess. Spray fields. And it's for 2 reasons that's not good. One reason, the strong magnetic field on the outside would damage this construction here. And it's hard to simulate. In order to reconstruct the results of our measurement, we have to simulate it. And some messy magnetic field is really hard to simulate. What we're doing now is by putting the iron around, we are forcing the magnetic field to stay within the iron. At the place where we are now, there's basically no magnetic field when it's working. Just, okay, there is a magnetic field, but some millitesla, while inside the iron it's 2 Tesla, and inside the coil 4 Tesla. The iron is the heaviest part of CMS, 12,000 tons. It's enough iron to rebuild the Eiffel Tower, just for scaling. The complete detector has an overall weight of 14,000 tons. And yeah, inside the coil, the next stage is the calorimeter. You can see the back of the calorimeter there, some of it. It's really hard to see at the moment inside. And really in the inside there is a tracking device, our tracking detector. We use this to measure the tracks of the particles. Okay, the muon detection on the outside has some. It uses a special property of the muon. The muon is the only particle which can reach this part of the detector. All the other particles will be absorbed in the inside. But the muon really uses only less energy while it goes through matter. It's a so-called minimum ionizing particle. So, if we see a signal in the outside, we can be sure it is a muon. So that's good, because we do not only want to measure the energy of the particles, but we want to identify the particles. So, identifying muon is easy. On the other hand, it is not absorbed in the calorimeter. So we cannot measure the energy. But we can measure the momentum. Because due to the magnetic field, the tracks are bent proportional to the momentum of the particle. But if the particles are really high energetic, the bending will become less and less. So if you have a really high energetic particle, the track will basically look like a straight line. And then it's really hard to say anything about the momentum. This problem is not there for the energy measurement, because if the particle is stopped, it's even better if it has a higher energy, because there's more light and you have more statistics to measure this light, and it's really good. Yeah, but for muons we cannot do it. But because we have a lot more space on the outside, we see more of the track. Even if a track is only less bended, but if you see more of the track, it's again easier to see. So that's one of the reasons why it has to be so huge. We have 14 meters diameter.
Podéis poner la cámara, porque tenéis un CCD, que es un CMS en pequeñito, y vais a hacer las fotos y ponéis en modo disparo múltiple. Entonces, podéis hacer 20 fotitos y se os cansa el dedo y luego podéis hacer otras 20, así en 3 segundos, ¿vale? Ahora, imaginaos esto, con apagado, funcionando, donde el CCD es CMS, hace el mismo ejercicio y hace 40 millones, eso hace 40 millones de obturaciones por segundo, pero no durante un segundo, durante 20 horas al día, 250 días al año, ¿vale? Eso encoge el estómago, ¿vale? Y otra cosa que podéis hacer es, mirando ahora desde ahí en perspectiva, el que quiera puede cerrar los ojos, pensáis en el event display, el dibujito ese de ordenador con las trazas del bosón de Higgs y eso, y veis lo bonito que es una cosa así, y lo abrís, y en realidad eso no ha pasado en el ordenador, eso ha pasado ahí. Los muones del Higgs han atravesado estas cámaras. Hemos creado una partícula que lleva 14.000 millones de años sin existir, y la hemos vuelto a crear nosotros, y la hemos hecho ahí en el medio, y se ha desintegrado en 10 elevado a menos 21 segundos, y sus cenizas han viajado a la velocidad de la luz a través de estos detectores, y nosotros la hemos cazado al vuelo y la hemos registrado. Eso. We created it. Just not there by chance. You made it.
We made it.
It was the more impressive when it comes to
Es impresionante, es bueno, lo mejor en el mundo.
Y vais viendo, si veis la forma de esto que se ve, lo negro es helical, lo otro es helical, de fuera también lo ves ahí. De fuera hacia adentro veis la forma cónica, pero también lo veis en forma radial. La parte más de fuera es helical, luego veis la parte de papel albal, si queréis, que se ve ahí justo alrededor de lo verde, es helical, el barril, y luego dentro, la zona verde, es el tracker. Y más dentro estará el microvértex. Y lo que veis por ahí ahora mismo es...
El tubo.
Bueno, el tubo de látex es un poco más estrecho, es el envoltorio del tubo de látex. Exigente que sube.
Bueno, y también
Acabamos a hostias, ¿eh?
Bueno, ya, pero porque se con mucha tensión.
Sí, porque además nos venían los datos del LHC y no era la que se puso, pero mira los